Now, we got a focus on some examples of early warning systems in different countries. First of all, we have a presentation from Alejandro Clement. Alejandro is the manager of Plankton Adeno in Chile, and the company undertakes a wide range of water quality analyses, including bio-optical sensors that they use to monitor harmful algal blooms. And I'd like to ask Alejandro to switch on camera and then take the floor.
There we go. We're ready.
That's great.
Okay. Good morning for some people in the chat. Good afternoon or good evening to others probably. So I prepared this talk with the help of all the people who work with us, which are most of them in the list there in the first slide. And I will like to talk about, obviously, HAB and early warning system in Chile, and basically showing you our experience. Can you go to the next, please, Ross? Well, I appreciate very much the invitation of you guys to this workshop. I've been very interested in this area. Desalination plants is an issue that is becoming very important in the northern part of Chile too. So we have some common things there in terms of water quality for desalination plant. Next. The general objective, next please, or enter in this case. And then the general objective is to share with you the Southern Chile experience of our group, because there are obviously many research going on HAB in Chile, but to share with you our work for many years, basically on monitoring, research, and some progress that we are doing in early warning system, which focus on aquaculture and also on water quality. Next, please. Some few examples, very important examples that we find in the literature or in internet is the early warning and prediction system of US, the Great Lake. The next, please. The Great Lake is doing a very interesting work, because in the Great Lake in northern US, they have a lot of problems in the big Great Lakes. Next, we can see, you can go ahead, Ross. Also, there are some in UK, there is a paper published by Davison, which I think it will speak next to us. And there is also an interesting area that they're using genes as a HAB early warning system. There is a group in Chile that are doing a research with Japanese money to study genetics and HAB forecasting. So there are several intentions to understand HAB from different point of view. Next, please. And next. Well, as you know, we are located in the Southern Eastern Pacific. Jorge made a really good explanation of all the oceanography in the coastal zone and the importance of the west wind drift and all the oceanography and climatic conditions that are involved in the oceanography and the biology of HAB. We are located in 3 places. Puerto, can you just please enter, Ross? In Puerto Varas is one lab, in Castro in the archipelago. Please press enter, Ross. Go ahead, 3 enters. And Puerto Varas. En Coya. Okay. Next, please. Well, this is a brief outline of what we are going to talk in this session. Basically, if we want to have an early warning system, we need to have intense monitoring on space and time. Second, we need some tools to work and to know a little bit about the biology and molecular biology of the cells. Also, as I will explain briefly, that we have developed a HAB-F index to have a better assessment of the risk. Most of these things are today in YouTube, so you can have the link is in the slide, so you can consider all the details. We are improving very much all the informatic issues as a general, like Python codes, SQL, building APIs, BI capabilities, and a lot of data analytics. On the other side, we are developing a bio-optical aqua sensor system to measure online and real-time water quality. So we will see all this in the next slides, please. Well, this is a tendency that we have seen very, very dramatically in Chile. And as you can see, the last year, the 2021, we have one of the driest year again. So the precipitation anomaly is becoming a very real issue, which is at least is the first driving force that produced the HAB. Next, please. We are using remote sensing just as a tool to have a synoptic view. These are images of last week. You can see at least two big features. One, cold waters in the coastal zone due to upwelling, and on the other, in the inland sea, you can see very high chlorophyll values due to protocentrum and some diatoms. But if you do zoom, you cannot have a really good resolution due to different reasons. These are algorithms that are not developed for inland waters, inland marine water, where you have a lot of noise from an optical point of view. But at least it can show you a very synoptic view of the area. Next, please. These are some of the cells that are growing this season: Heterosigma, Protocentrum, Lepidodinium, Cochlodinium, Iseuchatonella. These are not the bad news, of course, but I will show you more details on next slides. Go ahead, please, Ross. We are using also FlowCam to have digital libraries of dinoflagellates. It works very well with single cells, but when we have change, we have to do some arrangement to have a better number of the total number of cells. But it's a nice technology to have a database with the features of the cells and to improve the detection and to do a faster monitoring system. Next, please. Go ahead. Well, the HAB index for this analysis is an algorithm quite simple that we described the mathematical part here. So it's an average of the water column, as you can see in the left side. And also it divides the average value of a critical, the average value of the concentration of an harmful algae divided by the critical value. And all this is multiplied by some weighting factors, depending the type or the species, if it's a very toxic species or it's a less toxic species. It has been a very useful tool for our system. We have this algorithm in our server, so we can run the data on time historically, and we can check, and it works quite well. Now we're working in the range of the critical values for early warning. And so can you show please the next? We are doing some prediction of the HAB-F index. Here is just an example of a code that we are running, and the variables that we are using to have a prediction. We are using one of the base that has more data. We did first a screening of the data quality, the data in terms of time and space. So we have chosen already a place, and we are running this algorithm to forecast the FAN index. I mean the HAB index. FAN is in Spanish, sorry. Next, please. So the range that we have developed as a first approach, because this can be improved when we will have more data analysis. But until now, we can say that the green obviously are all those values less than 1, which is non-risk at all. But if you have a value of the HAB index above 1, you have, like in the football game, a yellow card, and so forth. And we define after 25 is a high risk value. This has been checked with real fish kills in the field, and we are correlating both to check if these risk values are adequate. Next, please. Next. We are also running an app with the information of the monitoring program. This app is almost a year already. Here you can see in the middle the HABF index in a large area, about 400 kilometers long from Puerto Montt to the Kupkeland Fjord. And you can see the numbers, very low numbers, all less than 1. That's a very good situation. And on the other one is the salinity, very low salinity in the eastern side, and of course higher salinity in the western side, which is in relation with the coastal zone. Next, please. Ecophysiology. We are trying to use ecophysiology as a tool, basically ecology and distribution of the cells in thin layers, data collection of photosynthetic parameters. We would like to have real-time data nutrients and ratio. I think the technology today is available, like nutrients on real time and silicate in real time. And I think it's our next step, probably in the next few years. Data analytic and modeling biological parameters like in vitro growth, photosynthesis, and stage of the cells or apoptosis are things that we believe are really interesting to know, to forecast the decay of a bloom. So, and obviously ecological parameters like competition, niche occupation, and among others are really, really important. And I think that the many researchers are coming back to these issues to understand better and to forecast better the blooms of the blooms. Next, please. Well, this is just an example of the distribution of photochemical parameters in the Pseudo-Chatonella bloom of 1916. As you can see in the left side, fluorescence, FOFM from a fast repetition rate fluorometry induction curve. And you can see that the highest photochemical parameters are coherent with the highest abundance of the Pseudo-Chatonella cells, but not necessarily are in the surface. It's in a thin layer around the 10-meter depth. Next, please. This is an example that the bloom that we are studying right now, and you can see in the table the abundance of Protocentrium micans and the abundance of Leptocylindrus and the photochemical parameters of FO and FM, which means initial fluorescence and maximum fluorescence of induction curve using fast rate fluorometry. And the next slide, please. Or go back one. Go blank, please. You can see in the top right of a map where you can observe the 4 stations in the section where we study this bloom that is going on right now. We have a lot of abundance of Protocentrium in the Reloncaví Sound at this moment. So next, this is a sampling that we did last week. Please, next slide. So what I did here, a very simple thing. I plot the FO in the left side and FM. FO is initial fluorescence and maximum fluorescence against the abundance of the Protocentrium mican cells. In the right side, you see the same parameter, FO and FM, against the abundance of Leptocylindrus danico, a diatom, also an harmful diatoms. But if you observe the R square values are, in the case of the dinoflagellate, are very high, so very well correlate the linear model. But in the case of the diatom, is very low, very, very low, which means obviously that statistically, at least, we observe a very good relationship between photosynthetic parameters, photochemical parameters, and the abundance of the dinoflagellate Protocentrium micans, and not in the case of the diatom. So most of the photosynthesis that is occurring in this bloom, despite that the number of cells of the Leptocylindrus danicus is relatively high, belong to Protocentrium micans. And that's a very interesting thing that I will show you in the next slides. Well, this is just example of blooms that we have been observing, as Jorge told you. In the left side, Heterosigma in the summer of 2021. In the middle, Lepidiodinium in January of this year, and in the right, Protocentrium. Next, please, Ross. Well, this is a table that of some features of the three main blooms that we have. Steuchatonella at the beginning of summer, a very strange bloom, low concentration, very toxic, very unpredictable. So it was very difficult to have an early warning condition because it was very unpredictable. We believe because we was very low amount of cells, as you can see, 163 cells per ml in very low abundance, and also probably in a very heterogeneity distribution on space. Lepidodinium is growing almost every year in summer, March, very large biomass, very photosynthetic, but is not creating any problem at the moment. Micans is growing right now, very photosynthetic, large biomass, but not as big as before. The maximum concentration is around, I would say, 8,000 cells per ml, but probably it will grow more in the next few days. So let's see the next one, please, Ross. Well, this is the distribution of oxygen. You can see in the bottom part a map, and station 1 is in the bottom part, and station 4 is in the upper part. So this is a typical oceanographic cross-section of oxygen against the depth and against the space. And you can see the distribution of oxygen is not homogeneous due to the distribution of fluorescence or the distribution of Protocentrium micans. So if you remember the plot that I did of photochemical parameters against cells abundance of the dinoflagellate and the diatoms, now I'm showing you the same data, but from CTD and fluorescence. And I can explain you that, Protocentrium is modulating the distribution of oxygen in all the water columns and the photic water column. See the next one, please. The next one, please. Next. Something is.
Yeah, I just got a technical issue here. I'm trying to solve it slowly. The presentation kind of suddenly froze.
Oh, you can press enter.
Yeah. All right.
There you go. There you go. There you go. This is the distribution of fluorescence. This is a wet lab, almost new, 1 year old fluorometer. So I believe in that data. And you can see the distribution of fluorescence and the distribution of oxygen, and it's very similar. So it's very coherent, the distribution of those both variables. And this fluorescent or chlorophyll belong mostly to Protocentrium. Next slide, please. Well, this is a apparent oxygen utilization. Again, the same feature of fluorescence and oxygen, of course. But the important thing is that Protocentrum is modulating the distribution of oxygen in the photic zone at different stages in very short space. Like here in station 2, you can see a subsurface peak, I would say, of apparent oxygen utilization, and station 4, you see it in the surface. And the distance of this is about 4 kilometers, very short changes. Next, please. This is temperature to finish the section, and let's go to the next one, please, Ross. Well, the bioptical aqua sensor is another technology that we are developing using Chelsea Trilux sensors and others also, Chelsea from UK. And basically we integrate, and we want to measure chlorophyll online and in real time, phycocyanin, which is tough, and turbidity, and hydrocarbon. All sensors that are pollution free, and we can measure in situ, and we have developed the software to have the real-time and online data. Please show the next one. This is basically our system, very simple. We use solar panels, batteries, the sensors, in situ sensor, mobile communication, smartphone to have internet, Panasonic computers that are very tough computer for field, or Raspberries, which are very cheap, but they are in rough weather cannot work well. All these go to the server in our system, and then we output the information with the app, and also using Power BI as a business intelligence system. And we use a web page. And here we can produce a early warning system when the amount of chlorophyll or hydrocarbon also can go above certain limits. The next, please. This is an example. Also, this is an example in the left side. This is data that is from yesterday. I don't want to, there is a link there, but I don't want to read it on time, in real time, because we might have problems. But in the left side is the data from yesterday and of chlorophyll, turbidity, and phycocyanin. As you can see, the data has a lot of peaks. So in that sense, we are now working data processing outliers. This is done by Martín Contreras and Álvaro Jorquera, which are our data science, and they are trying to develop an algorithm in Python, so we can do it on real time, remove the outliers on real time. At the same time, we are showing the information in the display, which is a very nice work, and it's very interesting because all this time series, it has a lot of noise, and we want to remove the noise using, of course, data science. Next, please. This is a brief diagram that shows our early warning system and alert. We received from the fish farm samples and information. We process the data in three labs. We put it all in a local server. We add to this information from Chilean Meteorological Service, NOAA remote sensing images, and we concentrate at the end of all in our HAB-F index, and we produce automatic early warning alert when the values of the HAB index is above certain number. Also, we can have visualization links using Power BI, which are automatically sent by WhatsApp or by email or in a web page. Next, please. Well, this is just an example of mitigation, which is in local waters in Chile, which is a very big issue. We have to work more and more on this as the techniques show clay. In this case, is air bubbles. Is a lot of engineering going on here and hydraulics. And we need to understand better the biology of the cells when they produce this technology, mitigation technology, to avoid the cells into the cages. And the last one, please. Well, some key ideas. Early warning system is a practical and operational approximation to decrease the risk. But the bloom and cells condition of dinoflagellates in general modulate the shape and flux of oxygen and the other features in the stratified water columns. Local variability in patches and vertical distribution, like thin layers, complicate the forecasting. As you can see, the section of chlorophyll, when you see a patch in the surface, you believe that that's only the patch, but what we are showing you with the cross section, that you can have a patch in one side, but the bloom in the other side is a 10-meter deep. So we have to be careful when we're looking from the air, like a drone or with remote sensing. No doubt that the cross section or water column analysis has to be part of the issue. Well, I think I will stop there, and if there is any question, very welcome to answer. And thank you very much for the invitation, Ross, and it was a pleasure to talk to you guys.
Thank you very much, Alejandro. That was a fantastic talk. Yeah, so could we have any questions, please, via the chat or directly? Seeing some very complimentary remarks there, Alejandro. Anybody want to take advantage? One question, and then we'll move on. I'll just ask a very quick one. So you think the kind of differential response of dinoflagellates and diatoms to that kind of fast fluorescence, would that help discriminate? Do you think dinoflagellate blooms?
Well, I think there are two physiological things going on. First, the diatoms are dying, to say it simple, when you observe in the microscope, or when the girls, they observe in the microscope, sometimes they have very low chlorophyll per cell, or you see only the frustules of the cells. So, and on the other side, but I think the most important thing is that when we have a bloom, obviously, not because we have a bloom, because these machines, biological machines, are doing very highly photosynthetic performance. So we are measuring when you have a bloom, these cells are doing the best they can from a photosynthetic point of view. That's because they are dominating the water column. And you can have 10 cells of diatom and 10 cells of a dinoflagellate, but the dinoflagellate is blooming, biologically speaking. And that means that has a lot photochemical parameters, a very high efficiency in photosynthesis. So I believe that the blooms have to understand from a photosynthetic point of view a lot better than probably have been done, because most of the time they try to explain bloom with mixed sulfur-free and things like that. I think we have to go into photosynthesis.
Yeah, I agree. Thank you very much. Thanks again. So yeah, we're going to move on to Southern California and somewhere a little different. I'd like to introduce our next speaker, and this is Professor Rafe Kadila. Rafe's based in the Department of Ocean Sciences at the University of California in Santa Cruz, and he's led development of the ocean observation and early warning systems for HABs all along the Californian coast. He's served as chair for GeoHAB, which was the predecessor of Global HAB. And I'd just like to, give the floor to you, Rafe. Thank you.
All right. Thanks you, Ross. And thanks to all of you for attending and for inviting me to talk a little bit about some of the systems in the US. And so I work primarily in California, and I will touch on that. But I really want to talk about three systems that have successfully transitioned from primarily research to operational systems that are ongoing and maintained over several years. And so next slide, please. And so those three, we just heard about Lake Erie, the Laurentian Great Lakes, California, of course, my backyard. And then I'll also talk about a little bit up the coast on the west side of North America, the Pacific Northwest program. And so they're a kind of backward order there. I'm going to start with the Pacific Northwest and then go to Lake Erie and then finally to California. So next slide, please. And so we start with the Pacific Northwest. This system is dominated by mesoscale oceanographic processes. And so it's an eastern boundary current system. Of course, the entire California current along the west coast of the US is an eastern boundary current system. And because of that, the primary interest is in tracking blooms that are starting in certain hotspots. And so the blooms that we're particularly interested in are Pseudonychia, produces domoic acid. And in this cartoon in the center, there's a couple of known locations where they start. One is the Juan de Fuca Eddy to the top, and the other one is Hecata Bank in Oregon to the bottom. And then they're transported along the coast and strongly influenced by the Columbia River plume. And so this project basically wanted to know, can you make a predictive system where the primary impact for this region is toxic cells getting to the beach and really impacting recreational harvesting of shellfish. And so this project has been running for a number of years on the right side, and I know it's very hard to see, but one thing I want to emphasize for all of these programs is that really the key outcome is an interpreted data set. And so not just simply giving you images or giving you raw data, but explaining what it means. And so that's an example of a weekly report that comes out from this program that goes to the managers and to other interested parties that describes the oceanography, gives a prediction of whether it's going to be problematic or not at the beaches. Next slide, please. And so the way they're doing that is it's the Pacific Northwest. If you're at all familiar with it, satellites are problematic because it's often very cloudy. And so instead, they've gone to a very sophisticated numerical model. And so here we're just looking at fields of salinity, temperature, biomass, and then also bottom oxygen through time. And what's really driving this system is the alternation between upwelling and downwelling. And so the upwelling drives the blooms. And then when we get downwelling conditions, it basically allows those bloom populations to be exported from those hotspots like the Juan de Fuca Eddy and transported down coast. And during downwelling events, they can actually get all the way to the coast and then cause problems. And so we're less concerned if the bloom stays offshore because there's likely impacts, but it's not directly impacting commercial harvesting or recreational harvesting. Next slide, please. And so basically what the system is doing is it's using that model and it's putting particles into it. And then we're looking for these source events. And so those green sort of streaks, those are sources of algae coming down coast in that case and impacting the beach. And then if you look at the sort of middle panel where it's got the red line, that's the cell abundances that are actually getting to the beach. And so this model does quite well at predicting the transport. And because it's a transport process, it gives you order of a week notice that oceanographic conditions change. It takes about a week for those cells to get to the shore and then to accumulate in the shellfish. And so there's actually a reasonable lead time on the predictability. Of course, this is only predicting the transport of cells. And so what's super helpful is they've been putting instrumentation like the environmental sample processor, which is basically a lab in a buoy that's sitting up in the Juan de Fuca Eddy. And that gives them information on whether those cells are toxic. And so then they can couple that to this transport model and say, yes, there's toxic cells, and yes, they're coming down the coast, or no, they're moving offshore. Next slide, please. And so if we go into the Laurentian Great Lakes, these are in the northern part of the US bordering with Canada. And in the US, they're large enough lakes that they fall under the marine system. And so they're operated, the monitoring and research is primarily conducted by NOAA. Next slide, please. And so this was widely identified as a problem a few years ago where this is Lake Erie in October 2011, and the green there are cyanobacteria. And so the major impact here is that it's getting into the drinking water systems. And so it shut down the entire city of Toledo for a number of days because microcystins were actually breaking through and getting into the drinking water. And so the real goal here, beyond just understanding where we have blooms and why, is tracking them to know if they're going to impinge on the drinking water intakes. Next slide, please. Yeah, just keep going forward. Can get to the next one. There we go. And so what they're doing is they're forecasting these blooms, and in that area, remote sensing works well. And so they're looking at a signal of the presence of phycocyanin in the water, which is unique to the cyanobacteria. And something that they're doing, which is a little bit unusual, is they're taking that kind of gappy satellite data, they're turning that satellite product into a density field, and so that sort of black dotted looking thing in the middle, and then they're running a transport model with that. And so they're doing a particle transport model and allowing the model to fill in everything, and then they analyze that. And so again, a key point here is they're not just giving you a map. They're not giving you particle fields. They're giving you an analyzed report that says, this is what's going on. These are the data that we're analyzing. This is what we think is the likely problem that you're going to have. And again, because it's a transport model, it gives you some days of predictability because we can see these blooms moving around within the lake. Next slide, please. And so this is just a little bit more detail of what it looks like. And so if we start on the left, they get a satellite image that's converted to particles in panel B. Those particles are moved forward in time, and then those particles are turned back into a color image because it's easier to look at colors than it is to look at a bunch of particles. But again, the key point here is that's not what they give you. What they give you is the document on the right, where they give you a summary of the image and then an interpretation of it. And so it always comes with interpretation. It's not just simply the data itself. Next slide, please. And finally, moving into my backyard, the California system. Here, what we're looking at is on the left, that sort of dot plot. That was the very large Pseudonychia bloom we had in 2015 that extended across the entire West Coast, shut down numerous fisheries, billions of dollars in losses to, for example, the Dungeness crab industry in California, Oregon, and Washington. And we've developed a system called the California Harmful Algae Risk Mapping System, or CHARM, that's focused, again, primarily on Pseudonychia. Next slide, please. Go forward one more. I forgot I had that in there. And so this one is a little bit different. On the left is our schematic, and it is, again, an operational forecast. But what we're using is a combination of, excuse me, a numerical model and satellite data to make statistical predictions of where you're likely to have high biomass and where you're likely to have high toxicity. And so what comes out of that are images like on the right, where it's a probability going from 0 to 1, saying, are you likely to have toxin there? And we run this model as a nowcast real time and as a 3-day forecast, and then finally as a seasonal hindcast. And what we're working on now is taking those seasonal hindcasts and starting to project them forward, looking at what conditions are likely to be in the next year or 10 years or even 50 years. And so next slide, please. And so, but again, we don't give that sort of underlying data to the end user. Instead, what we do is we produce a bulletin. And so this is just some examples of the bulletin, but the bulletin is pulling in more than just that forecast. We pull in marine mammal strandings, data from the state of California on actual toxin levels, example images showing what it's like now, what typical conditions are, whether we should be concerned about this or not. And so again, emphasizing that, you know, the primary outcome is to give you guidance, to give you documentation, not to just give you the raw data. Next slide, please. And so thinking about the rope me area, this is a project that goes back a few years, but Don Anderson led this. And we actually worked in the Sea of Oman and the Arabian Sea to try to look at, similar to what DISCO and some of the other programs we've heard about have been doing, what would a system look like in that area? And again, what we emphasized is you can't just simply hand somebody the raw data. And so this is an example of the very large Margolefidinium bloom. And we started with the satellite data. And so the smaller inset images are showing you some of the Modus Aqua data, but turning that into a red tide probability. And I won't get into the details, but we're looking at spectral signatures and biomass and trying to identify, say, a dinoflagellate bloom from other types of blooms in the area. And so what we end up with on the left is just simply a binary where you see white. That's a very high probability that's a red tide. And then on top of that, we've taken a numerical model and put the vectors on that. And we can start to tell you the transport outcomes for that. This is a relatively low resolution version. What we ended up with was using a model called FVCOM at very high resolution and targeting very specific locations. And so we were very successful looking backward as an example of looking at, say, the Barca desalination facility and identifying blooms that started a little bit offshore and were likely to impact that facility. But again, the point here is that you don't simply give people the raw data. You give them an interpreted product. You say, this is what we think is likely to happen. This is our confidence in our ability to predict this. And this is where we're going with this sort of analysis. So next slide, just wrapping it up here. I'd like to emphasize that operational does not mean static. And so in all of these operational models, there's this constant iteration of improving things. And so in California, we're building out a network of 10 to 12 imaging flow cytobots that can both ground truth automatically, that can tell us what cells are there, but we can also start looking for cells that are not high biomass. And so we can pick out dinophysis and some of the other ones that cause problems, but aren't going to show up in a satellite. And the other thing that we've been doing is moving away from purely statistical models and moving into a physiological mechanistic model. And so trying to get at, well, why are these blooms occurring? What are the drivers? Is it nutrients? Is it upwelling? Is it something else? And so I believe I have one more slide, and then I'll stop here. Two more, sorry. And so really what I want to emphasize is we've seen a lot of these sorts of diagrams, and I just want to emphasize that bottom square that says user requirements, that there absolutely has to be this feedback loop. You can't just simply produce a report or produce a product without verifying from the users that it's actually useful. And then if it's not useful, figure out why and address that. And so one more slide, and this should be my last one. Great. And so my take-home message is that really, if you want a successful program that can go beyond research and get into operational status, it needs to be fit for purpose and it needs to be useful. And so it absolutely has to be based on good science. If the scientists don't believe it, it's not going to be useful. It has to be vetted by users. You can't have it be reliant on a single person or entity because it's not going to be operational if that's true. And you absolutely have to keep revisiting it and saying, is this actually useful for users? If not, can we improve it? If we can't improve it, maybe we should stop spending money on it because it's not being used in the way we thought. And so I'd just like to end there and thank you and acknowledge the many groups that have contributed to both the research and the programs. Thanks.
Thank you very much, Rafe. Fantastic talk. And yeah, we'd just like to offer the chance to the participants to ask some questions. I can see some questions there, but I think they relate to previous talks. There's a question about bubble technology. Yeah, that definitely, I think, is a previous talk.
Well, I'm happy to bring us back on schedule or closer to schedule. And I'm also happy to, I think you have my email, I'm happy to answer questions.
Okay.
As well.
I'm sure that we're going to.
I have a question.
Oh, yes, please, Alejandro.
Hola, Rafa.
How are you doing, Alejandro?
Fine. What is your point of view, or California people point of view, in relation to climate change or climatic anomaly and HAB?
Great question. We're quite interested in that. We're actually running 50-year simulations looking at what it's likely to be in the future. And it's absolutely going to, we see an increase in Pseudonychia, for example, as well as moving north, more into Washington and Alaska. We're also quite concerned about multiple stressors that we're seeing simultaneous impacts with climate change of low oxygen, as well as more harmful algal blooms and of course warming. And so very concerned that, it's going to shift things northward, and it's also going to move us out of our sort of comfort zone where we understand the system, and we're seeing more unusual events as the climate is shifting.
Okay, thank you very much.
Yeah, thank you very much. Okay, we're going to move on to the next speaker. And I'd like to introduce Professor Patricia Gleibert. Patricia is based at the Center for Environmental Science at the University of Maryland, and her research focuses on nutrients and harmful algal blooms events. She was a member of the Global HAB Scientific Committee. Thank you, Patricia. Over to you.
Well, thank you. Thank you to the organizers for the invitation to give this talk. I also want to thank all the other presenters for such excellent talks, and what an excellent conference this has been. Wishing we could meet in person. I'm sure that day will come someday. Well, I was asked to talk about development of early warning systems and future projections for Asia. And I want to first talk about some of the changes and complexities of HABs in Asia. Next. Well, one of the complexities, of course, is that Asia is a very large place and there are many causative species. There have been a number of excellent review papers in the last year or two summarizing these data. You can see for China, Karenia is one of the major species, whereas in Japan, Margolefidinium, Chatanella, Karenia, and Korea, Margolefidinium, or what we used to refer to as Coclidinium, is a major problem. Next. When we look to Southern Asia, many of the fish-killing species are those same species, Chatanella, Margolefidinium, and the Karenias, whereas also the PSP species, Alexandrium, Pyridinium, and Gymnodiniums are also problematic. Next. Here, Sakamoto et al. Summarized the government reported data for China, Japan, and Korea. These are the recorded red tide incidences and the economic losses to fisheries. And you can see a number of trends. First, from 1970 to current day in China, there's been a huge increase. The economic impact depends on which species at which time is blooming. The Ceto Inland Sea has seen a decrease, and this is a fairly well-reported story. And Japan and Korea, somewhat consistent trends over these decades. Next. If we focus on China, there are a number of papers that have recently used the government statistics to show that there is some potential good news. That is, since about 2005 or so, the number of recorded red tide incidences have decreased, as have the economic losses. Next. Well, if we now step back and ask what are the causes of the increases that we have seen, and I'm going to focus now on China. Here are the changes in nitrogen and phosphorus inputs from 1970 to 2010, and you can see, no surprise, these inputs are very large. Next. And relating the number of HAB events in the different regions of China, whether it's the Yellow Sea, the East China Sea, or South China Sea, relating those HAB events for these decadal patterns for nitrogen in the top panels and phosphorus in the bottom panels. Those relationships are strong. So there's no question that nutrient pollution has been a major causative factor for the increase in these blooms over this decades. Next. But one of the interesting relationships is that if we look at the number of HAB events, either per year in the top panel or per year spatially explicit in the bottom panels, and relate this to the nitrogen to phosphorus ratios, we see that these blooms really occur only when the nitrogen to phosphorus ratios are elevated. So nutrient ratios matter. It is a nitrogen problem more than a phosphorus problem. Next. We can also look at the apportionment of nitrogen and phosphorus changes for these three regions of China from 1970 to 2010. And you can see clearly the huge increase from 1970 to 2010, most of which is due to riverine sources, most of which is due to, for nitrogen, agricultural inputs. For phosphorus, there's a greater point source input, that is the part of the blue bar that's not speckled. I've circled here the input of nitrogen and phosphorus that's due to either river export due to inland aquaculture or nitrogen and phosphorus to the sea region from marine aquaculture. Next. Focusing on the inland aquaculture, which is that portion of the circled bars for the left side of the panel, we can see the change in inland aquaculture from 2006 to 2017 in terms of total production, in terms of nitrogen release, and in terms of phosphorus release in the lower panel. Next. The same for marine aquaculture, we can see the change in total production, the change in nitrogen release, and the change in phosphorus release. So aquaculture is not only affected by HABs, it's contributing nitrogen and phosphorus to the system. Next. So we're interested in advancing prediction. And we've heard a lot about all of the new systems and advancing systems for data acquisition, whether it's satellites, whether it's molecular tools, in situ analyzers. We are acquiring massive amounts of data. We are also advancing models in many ways. We've heard about mechanistic numerical models where rate processes and exchanges between nutrient sources, whether it's between organisms and nutrient sources or between sediments and water column. These models are advancing in all systems. We heard about the California system and the Pacific Northwest, and we've heard about other systems in Kuwait where these are advancing very rapidly. We've also heard about machine learning models. All of these models are really wonderful new tools. One of the things that these tools are all giving us is the ability to predict chlorophyll with very high fidelity. Next. And just as an example, here's an example of a forecasting system for the Shenzhen city area of China using one of the machine learning tools to support vector regression model. And these are two particular days where chlorophyll was predicted. Next. But one of our questions is, how do we predict species? we can deconvolute chlorophyll signals from spectral analyses. But when we start to ask questions of mixed bloom assemblages, how do we predict one species relative to another? And numerical models get very complex very quickly when we start layering in many, many species. One approach is to use a rhomboid strategy, which is we characterize one species against a background of different functional groups. So for example, we characterize Margolefidinium against a background of a diatom community. Next. So this is just an example where we have a biogeochemical model that normally models 3 phytoplankton groups. In this case, modeling a very specific dinoflagellate, but modeling the other 2 as generic phytoplankton functional groups, either a diatom group or a nanoflagellate group. Next. Another approach is to model the habitat as opposed to the species growth per se. So we define a species niche based on what we know about that species preference for temperature, that species preference for salinity, for specific nutrients. And we can use the numerical model to predict when these conditions overlap, creating a suitable habitat. It doesn't tell us that that species is actually growing, but it provides a risk or likelihood that that species could grow under those conditions. Next. So we used this approach a couple of years ago to predict the change in 2 different types of HABs in Asia, Percentrum and Karenia. In this case, the future was end of century. We were looking at climate change impacts. And rather than actually predicting growth, we predicted the habitat change. So if we look at the future projection, we can see the northern expansion. It doesn't tell us that this is actually growth or growth intensity. It doesn't give us a chlorophyll map. Rather, it gives us a habitat suitability map. We can use this, for example, as a risk map. If we know the risk is going to increase, is this a site where we might want to avoid aquaculture, for example? Next. A similar projection was made based on a number of scenarios, looking at how those scenarios will change the total nitrogen to phosphorus ratio. And we can see here that projecting HABs in China will likely persist because the nitrogen to phosphorus ratio is not going to change substantially. Next. Another approach is to improve the mechanistic characterization of species when we define our species growth within a mechanistic model. Now, for dinoflagellates, and we've mentioned this a number of times over the last 2 days, many dinoflagellates are mixotrophic. Next. When they're mixotrophic, that means that they can behave plant-like. That means they can use inorganic nutrients and carry out photosynthesis, but they can also eat. And when they eat, they take in those particulate nutrients as particulate nitrogen, particulate phosphorus, particulate carbon. They also take in the chlorophyll from the prey, and in many cases, they can live off of the chlorophyll that the prey provides. So this adds tremendous complexity to our deconvolution of these signals in the water, because we need to take into account the chlorophyll that many of these mixotrophs are acquiring through eating. Next. Mixotrophy increases growth rate, and it can sustain growth longer when inorganic nutrients have become depleted. Mixotrophy often increases with increasing nitrogen to phosphorus ratios. So I come back to nutrient ratios matter, and mixotrophy and toxicity may be synergistic. That is, as the cells release toxin, it may harm the prey. That may in turn break open the prey, releasing dissolved nutrients, or it may stun the prey, making the prey easier to capture. Next. So here's an example of modeling mixotrophy, not in Asia, but in my own backyard of Chesapeake Bay. And this is carlidinium, one of our toxic HAB dinoflagellates. And you can see in the upper panel, it grows at least in the model, and this has been consistent with in situ data. In the early months of the year, shown in the red line, it grows autotrophically. That means it grows as a phytoplankton. And then it shifts to heterotrophic growth in the summertime. It shifts to heterotrophic growth when the prey increases, and you can see that in the middle panel, the blue line. The prey increases in May, June, and July. So it has plenty of food to eat. And this is also consistent with the time when nutrients, inorganic nutrients, as shown in the bottom panel, begin to decline, particularly phosphorus. So again, high nitrogen to phosphorus conditions, high prey availability, and the bloom can be sustained living off of prey. Next. So lastly, I want to make the case that when we develop these kinds of models, we can run in silico experiments, that is model experiments, where we turn on or off various multiple stressors. And this addresses the question that was raised to Rafe just a few moments ago. What happens under warming? What happens when we change nutrients? What happens under altered CO2 conditions or altered pH conditions, or with hypoxia? All of our various stressors that we know are changing rapidly, and we can use these models to turn on or off one or more of these stressors, as I said, singly or in combination. Next. So here's an example using our mixotrophic model to test the effect of future warming. And this is 50 years out. We can see in this case, this is our carlidinium model for Chesapeake Bay. Future warming is going to reduce the likelihood of this HAB in the middle of the summer. The warming is such that the temperature is outside the optimum growth window for carlidinium growth. On the other hand, if we look in the lower panel, prey is not affected by warming. In fact, prey may actually increase. And so if we turn only our attention to this one species, we'll say HABs are likely to be fewer. But this prey is also prey to other species. So it's likely that we will open a window of opportunity for other species. We can also look at climate-induced changes in riverine nitrate and phosphate loading. And here we don't see as much of a change. In this case, we didn't make as large enough change as necessary to reduce the nutrient loads to have a significant effect. Next. So some take-home lessons and grand challenges. Certainly nutrient pollution remains a grand challenge, particularly in Asia. and many parts of the world, some regional progress and potential good news, but more reductions are needed, and we have to pay more attention, especially to nitrogen. Aquaculture continues to be threatened by HABs, but also contributes to the nutrients supporting them. Regional and early warning models are advancing, but largely based on chlorophyll. And in order to predict HAB changes of individual species in a complex changing world, we're going to have to pay more attention to HAB physiology, and particularly for dinoflagellates, paying attention to mixotrophy. Some species are more mixotrophic than others, so we're going to have to acquire more data to add into our models. And a suite of different types of models, coupled physical, biogeochemical, HAB, multitrophic level models are going to be needed to test how stressors interact to project future HAB growth and future risks to aquaculture and other fishery resources. So thanks again to the organizers and to my co-authors and other researchers who were credited above on different slides. Thank you.
Thank you very much, Patricia. Another great talk. Okay, we're going to open to the floor for questions.
Can I?
Please do.
Can I?
Please go ahead.
Yes, well, a lot of information, Patricia, and I have several questions, but I will try to focus on two of these. When you say that they use prey and they use chlorophyll, it means that chlorophyll is active photosynthetically speaking, or is just a biological compound? I mean, they can use chloroplast like a symbiosis system, or what do you mean when they use chlorophyll?
Yes, so many mixotrophs are able to ingest prey and actively use the chlorophyll from the prey. We call this kleptochloroplasty, meaning stealing the chloroplasts. They digest the rest of the prey cell and continue to use the chlorophyll from the prey machinery.
Oh, that's great.
Yeah, so it gives the cell this advantage of living off of the prey chlorophyll as well as its own chlorophyll. In some cases, as in the case of Noctiluca, it doesn't even make its own chlorophyll. It just lives off the prey chlorophyll. But many species can live off of their own chlorophyll and that of their prey.
Thank you very much.
Thank you. We've got a quick question from Naresh here. Naresh, do you want to ask your question?
Hello, sir.
Hello, please go ahead. Ask Patricia your question.
Yeah, we are having like algae blooms yearly 4 times in Gulf of Oman. Like I was like checking for the algae blooms and regular monitoring of algae species in this one. So we want to do chlorophyll estimation. So what does this chlorophyll estimation help us in prediction of algae blooms? Can you give any suggestion?
Yes.
That's chlorophyll. I hope you got my question.
Yes, I understand your question. And chlorophyll is one of the major parameters we use to tell us whether a bloom is occurring. But chlorophyll alone doesn't tell us what species is present. It can tell us that a bloom is present, but it doesn't tell us what species. And we can have a mixed species bloom, or we can have a bloom of one species, but we don't gain information as to the particular species by only focusing on chlorophyll. Chlorophyll is a great index of blooms. Don't get me wrong, but it's only an index of bloom condition.
Okay, great. Thank you very much, Patricia. That was wonderful. I'm going to move on to the